Hi everyone, welcome to this video. I just wanted to make this because we had some technical difficulties on Tuesday with our equipment, so people were asking about this review session, so I will be posting it on YouTube. From now on, all of these worksheets that I cover in office hours will be uploaded directly to Canvas, so you can access those videos from there. So without further ado, let's just jump right in. So for 1A, given the following Illids, determine if the reaction will yield an E or a Z alkene. So in the Wittig reaction, we have these reagents called Illids, and it's just basically a molecule where there's the phosphorus carbon bond, and they both are charged species. So the phosphorus is positive, the carbon is negative. That is what an Illid is. All right, so the way that we determine whether or not these are going to form an E alkene or a Z alkene is to see if the Illids are stabilized by any sort of additional features like resonance or induction or things like that. So when we look at part A, we see that we have this negative charge at this carbon position, and we really don't see any sort of additional stabilizing features. We don't see resonance possible or induction that spreads. So this would be considered a Z alkene. Z alkene. Let's look at B. So sometimes you'll see Illids given in double bond, like alkene notation, and that's really just the same thing as if I resonated those electrons out. So I can draw this structure like this. And it's the same thing. So when I look at this structure, is there any way that I can additionally stabilize this nucleophilic carbon? Well, yeah, we have all these pi electrons in that benzene ring where we can do resonance stabilization or delocalization. So that means that this is a stabilized Illid, and that would form an E alkene. All right, in part C, let's do that same thing where we resonate those pi electrons out to see like the reactive notation of this Illid. And we have this type of molecule. So is there any sort of stabilizing features that can help stabilize that carbon? Well, it looks like there could be resonance, but be careful, there really isn't resonance. That pi bond, which is at this position, is too far away to actually be delocalized by those lone pair electrons. Since there's too many sigma bonds in between, we really can't participate in resonance. So this would also be a Z alkene. So just be careful. It looks like it's resonance, but it's not. All right, and that is 1A. So let's talk about 1B. So I'm sure you guys have seen or picked up by now that in this chapter we have a lot of discussion about equilibrium. And my rationale for equilibrium is just stability. So I don't really memorize anything. I just kind of look at my molecules, my reactants, and my products, and I determine what is more or less stable. So in part A, we see that we have this ketone, and we're doing a ketol formation reaction, and we see in our reagents that we are removing water. So that's a very key piece of information here. If we were to not remove water, the equilibrium would favor the ketone structure. So if it was not removing water, we would have this ketone because the carbon-oxygen double bond is very strong and very stable and minimizes the steric hindrance that we see in the ketol product. So if we look at this ketol product, we see that we have these two ether groups also connected to these two just arbitrary R groups. So that's a lot of bulky steric hindrance that we see with the ketol group. So it's not really stable in comparison to this ketone where the carbon-oxygen double bond is very, very strong and minimizes steric hindrance. So the way that we can push the equilibrium to these ketol products is by removing water in an apparatus called the Dean-Stark trap. And I'll be posting a video about how that apparatus works so you guys can kind of get a better picture of it. But because we remove that water, the equilibrium will be driven to completion or to the right and form that ketol product. All right, so if that water was not taken out, we would not form the ketol. We would stay at the ketone product, or the ketone reagent, sorry. Let's look at B. So B, we have a ketone product, and we're adding water, and we're forming this gem diol. And if you recall about hydration of ketones, these are not favorable at all. The only time that it is favorable if I have formaldehyde, where these R groups, instead of them being R, like a methyl and an ethyl group, they're both hydrogens. Since those hydrogens are not bulky carbon groups, the steric hindrance isn't as common. So if I can just draw what a formaldehyde structure would look like, we don't really have steric hindrance because those OH groups can rotate and actually move around in space so that we don't really have any sort of bulky groups adjacent to one another. So in this situation, hydration is totally unfavorable, so we are actually going to favor the ketone product, so that would be to the left. All right, let's look finally at C. So C is just the second step of the preparation of Illids. So I don't know if you recall from the very beginning of Wittig reactions, this was the beginning of Exam 2 material, we could do nucleophilic attack with a triphenylphosphine with some sort of alkyl halide, which extends the carbon chain. And that last step in preparation of the Illid was using some sort of strong base like this butyllithium organolithium reagent to remove a hydrogen from this position and make it a nucleophile, at that position. So that's just a simple acid-base reaction that we see. So in this reagent starting material, we have a positive formal charge, and then in that end product, we see we have a net neutral 0 charge. So clearly net neutral, no formal charge would be more stable, so the equilibrium likes stable things, which would mean that it goes towards the right. All right, so we kind of just use this chemical logic of sterics and stability and maybe apparatuses like the Dean-Stark chart to rationalize where we can have our equilibrium lie. So that is 1A and 1B. Let's move on to 1C. So for the following molecule depicted below, draw the mechanistic arrows that collapses the oxaphosphatine ring. So in the Wittig reaction, we have this key intermediate. It's this oxaphosphatine ring. Although you don't need to know the name of this ring, it is important to rationalize the mechanistic arrows and why some might go somewhere and some might go somewhere else. So clearly we are going to form an alkene in the Wittig reaction. And what happens is that the driving force of this reaction is the formation of that strong oxygen-phosphorus double bond. So I'll just draw the end product first. This is the driving force of the whole reaction. Forming this final end product is so stable because of how that oxygen-phosphorus bond. So what we want to do is show that these arrows from this sigma bond is going to swivel over there, and then that exceeds the octet for the phosphorus, so then these must resonate back down. So your end product is going to be something like that. So you can see that even though we don't have any EZ geometry there, we form an alkene with the collapse of that ring. All right, hope that makes sense. So let's look at our first application problem. So nalemphine is commonly known as Revia. It is a drug that prevents relapses in individuals that battle alcohol addiction. So we realize that nalemphine can be synthesized by the Wittig reaction. So below I gave you the true structure of the nalemphine, and I gave you a shorthand notation because we're not going to expect you to draw out the full crazy structure that is nalemphine. So part A, propose the two starting materials to synthesize nalemphine via the Wittig reaction. You may use the shorthand notation in your response. All right, so let's think about the Wittig reaction. So typically, this whole chapter is carbonyl compounds like aldehydes and ketones, and later on we'll get into the derivatives of that like carboxylic acids, esters, etc. But we always know that we're starting with some sort of carbonyl group, and then we're adding in a Wittig reagent to form an alkene. All right, so that's the generic schematic of a Wittig reaction. So using those pieces of information, I can rationalize that this was my starting material. So these R groups just come for the ride because we're not really doing anything there. So we must have started with a ketone at that position, and then my Wittig reagent was just an additional CH2 group, so it's probably something like this. And you can draw it either way. So I'm going to draw it like this, or you can draw it like this, or you can draw it like this. Okay, your choice. They're all equivalent. So that makes sense. So these would be the two starting materials. We can rationalize that oxygen is going to be replaced by the CH2 group that is on that Illud. Okay? Let's move on to B. So part B says just draw the mechanism between the reagents you drew in part A to synthesize nalemphine. So let me just zoom in over here. So nalemphine looks like this. So that was the starting material. So we had R, R prime, R double prime, and then we had over here some sort of ketone, and then we had an Illud. So PH3P, and I'll just draw it in the reactive notation. Okay, let's just switch colors here. So what happens is that since we have this Illud, those lone pair electrons that are on the carbon are available to do nucleophilic attack. Recall that we have a dipole moment at this position in this carbonyl where there's a slight positive charge of that carbon, classifying it as an electrophile, and we know that this is our nucleophile, the Wittig reagent, so if you draw this as the first mechanistic arrows, you are correct. So let me just draw the product of step 1. Okay, and we just formed a bond here. So CH2, PPH3. All right. So our CH2 group from here is actually at that little carbon over there, and what happens is now we have these adjacent anion and cation species, and they're very close to each other. So it would make logical sense that the mechanistic arrows would show a pair of lone pair electrons from the oxygen attacking that phosphorus, making a ring. So the end product of that mechanistic step would be something like this. Okay, so now we have this net neutral charge. We have this stable oxyphosphatine ring, or not really stable, but it doesn't have any formal charges. And remember, the driving force of this reaction would be the formation of that oxygen-phosphorus double bond. So those arrows would go there, and then that would go down. So the end product of this would just simply be this. Okay, so that makes sense. That's the lemphene, in its shorthand notation. We replace that carbonyl group with just a plain alkene, and that is that. So let's move on to the next question. So over here, so for the following reaction, draw a stepwise mechanism that accounts for the formation of the products depicted below. Use curved arrow notation and be sure to not skip any steps. So we have this ketone, and we are reacting it with a primary amine, and we are forming this imine. So an imine, I-M-I-N-E, is a carbon-nitrogen double bond. That is the key, versus an enamine, which is just an alkene plus an amine. So we would see the double bond not associated with the carbon-nitrogen. So if we were to draw the mechanism for this, we kind of have to rationalize the nucleophilicity of our amine. So remember, this whole chapter is about adding in different types of nucleophiles into carbonyl groups, and basically all we've talked about is the C's, the O's, and the N's. So we've talked about carbon-based nucleophiles with the organometallics. That was last exam. We talked about oxygen-based nucleophiles in this exam material, and we also talked about nitrogen-based nucleophile addition into this exam material as well. But the key difference between oxygen and nitrogen-based nucleophiles is the carbonyl group does not have to be protonated first when there is a nitrogen nucleophile being added in. And that is because the nucleophile of a nitrogen is a lot more reactive than an oxygen nucleophile, so we don't need to have that protonation step to activate the carbonyl to do a reaction. So that will make sense in the mechanism. So I'm just going to zoom in over here to see this better. So if I redraw my starting materials, it's going to look like this. And I have this amine. Okay, and the first step is that these pair of electrons can just add right in to the carbonyl group because those are a source of electrons adding into a partially positive carbon, and the products of that step would be this. And make sure you don't forget your carbon, so 1, 2, 3, 4, and that has a positive formal charge. So the next series of reactions are really simple. They are the same thing over and over again. They're just a series of acid-base transfers. So you're going to basically be removing protons from this hydrogen and from this amine group and giving it to the oxygen to make it a good leaving group. So I'll show the longhand notation of this, but then I will also show the shorthand notation, which is totally acceptable to do on the exam, and I actually recommend it, so you kind of don't have as much room for mistakes. So I can just take in another equivalent of primary amine, and these pair of electrons on the nitrogen will just grab off a proton and do this. So we now form something like that. Okay, and then what this is going to do is that now protonated amine, so it looks like this, can now donate that proton that it just grabbed from the nitrogen and give it to the oxygen. Okay, so the product of that step would be something like this. So we know that an anion leaving is not the best leaving group. We also know that OH is not the best leaving group. So, excuse me, I wrote that backwards. So this should be OH. And that should be this. Okay, so now we have hydroxide, so we're almost there. We're not quite at that good leaving group yet. So what we can do is take another covalent of protonated amine and add that into the hydroxyl group to make it basically a water functional group. So now a pair of electrons, we'll grab that hydrogen, and we are now left with a fully protonated molecule of water, which is a very good leaving group, and we are now left with this functional group. Okay, so recall that there's still a pair of electrons that are on that nitrogen, and what we can do is push those down, which kicks off our leaving group, and now we are left with an imine. All right, so the final step to this would be 1, 2, 3, 4. So we are almost at our end product, and that is just the final removal of that hydrogen. So we can just take an unprotonated amine available in solution, so like that, and just remove that final proton, and then we're there. Okay, so that is the long mechanism that you can totally show in the exam, but to save time and to hopefully not lose any more points, I'm just going to highlight the steps that I could have showed differently. So this step, and this step. So those 3 steps could have been condensed into something that looks like this. I'll draw it below in like another color. So you could have showed this end product here, and you could have gone directly to here by showing this. Okay, so that really condenses the mechanism a lot more. That tilde and that proton basically just means that we are doing a series of acid-base proton transfers between adjacent groups, and that's understood in the mechanism, so we don't really expect you to show that for this whole mechanism. All right, so I hope that makes sense. Let's move on to question 4. So question 4 is filling in the missing information. So this is something that students struggle on the most because it is kind of more critical thinking, not just predicting the products, but predicting the reagents or predicting the starting materials, which can obviously, rightfully so, be more challenging. So I'll just work through these piece by piece. So if I'm predicting the Illud reagent, so we're doing a Wittig reaction here. We started with some sort of carbonyl group, and we're forming an alkene. So basically, first thing I would do is locate that alkene in my end product. So that's clearly this alkene. And if I look at the carbon count of the beginning starting material, I see that it's a 2-carbon, starting material over here. So that's probably carbons 1 and 2 over here. And it looks like we added this entire carbonyl chain to it. So I can rationalize that by determining the easy geometry of this alkene, whether or not my Illud was stabilized or unstabilized. So if I were to classify that alkene, is it E or Z? Well, it is an E alkene, okay, E alkene. So that means that I had a stabilized Illud. So I'm thinking something along the lines of PH3P with some sort of 1, 2, 3 carbon group. 1, 2, 3. So something like that. So this is the Illud that I would predict that reacted with our starting material, because we are adding 3 carbons. So if I were to just do my carbon count right here, 1, 2, 3. So that would probably be 1, 2, and 3 over there. And we know that it's a stabilized Illud because we have an E alkene end product. So that would be the rationale for this step. Maybe another way that may not be clear is that they rotated around the sigma bond a little bit to orient it. So let me just draw that orientation. So it kind of is reacting like this. Oops, I don't know what happened there. It's reacting in that conformation. So that might be more clear on how you added the Illud from that kind of conformation. All right, let's move on to B. So we want to have the starting material for this carbonyl compound. So we see in the middle we're doing a Wittig reaction, and we look like we are forming an alkene at this position. So you kind of just want to look for like things that match up. So this whole group looks like it matches up to this whole group. So the right side must have been my starting material. So I could just copy and paste. So it looks like this. Oh, that should be an isopropyl group. It came out weird. All right, and that is my starting material. So it was an aldehyde. All right, so that makes sense. So always just check your, do a predict the products, I guess, with the starting material and your reagent and see if you get that final product. All right, so let's look at part C. So part C is some sort of aldehyde, and we're doing one equivalent of methanol under acidic conditions, and then we're doing another equivalent of methanol under acidic conditions. So recall that as long as we remove water, we can drive this equilibrium all the way to the acetal product. However, there is a hemiacetal intermediate, so although it's not isolated in solution, this question just wants you to show that you understand what one equivalent of methanol added into an aldehyde, or the hemiacetal synthesis would be. So the hemiacetal product would be something like this. Okay, and then you can rationalize just adding another equivalent would remove that hydroxide group, so it would be something like this. Okay, and this is actually the final product that we see in mixture as long as water is removed with the Dean-Stark trap. So that is the acetal product. But we do have this hemiacetal intermediate, so this is something that you could see on an exam. All right, so finally we see that we have a carbonyl component. We don't know this reagent, and we're forming this nitrogen ring on top. More specifically, if I were to label or classify that functional group, I would classify it as an imine or an enamine. Okay, well, it's an enamine. So the word enamine actually is a combination of the two words alkene, so double bond, and amine. So if I see an alkene and an amine in my molecule, I know that it's an enamine. So just a little bit of recap. Primary amines will yield a imine, which is a carbon-nitrogen double bond, while secondary amines will yield an enamine, which is a carbon-carbon double bond and an amine. So I'll just write carbon-carbon double bond. Just some knowledge to recap. So clearly, if I form an enamine, I must have had a secondary amine starting material. Well, look, it looks like that's my secondary amine that I added right there. So I can just copy and paste that as a reagent, and that's my answer. Just as simple as that. All right, so I hope that made sense on filling in this information. So let's go on to predict the product. So we're going to draw the major stereoisomers of these. So from now on, I just want to make a note here. We are going to see a lot of reactions that can happen intramolecularly, or within the molecule itself, and not a separate reagent. So that's just something you need to be cognizant of. Always look for ring closures or ring openings. So we will see a couple of examples here. All right, so right now, if I were to just look at number 5, we see that we have a couple functional groups in this molecule. We have an alcohol, we have a ketone, and we have an arene. And under normal conditions without that acid present, it would just be in its normal state right now, that starting material. But the minute that I associate this molecule into acidic conditions, an intramolecular ring closing happens. So recall that we can realize that this is going to close a ring because this is an oxygen-based nucleophile adding into a carbonyl group. So if I were to classify this, and I'm just going to use the letters N and E here, the hydroxyl group, is that a nucleophile or an electrophile? Well, that's a nucleophile because they have a series of lone pair electrons that can add into a carbonyl group. And remember, we rationalized with the electronegativity of that oxygen that we have a partial positive on that carbon, so that's an electrophile. So we can do a nucleophilic attack reaction with this molecule, all right? So I'm just going to erase here and show you what that acid does. So remember, I said earlier today that nitrogen-based nucleophiles can directly attack into carbonyl groups because they are a stronger nucleophile compared to oxygen. So oxygen-based nucleophiles are not as strong, so we need to do a step first before the reactions happen, and that is the role of the acid. And the role of the acid is to just protonate that carbonyl group to make it more electrophilic. So a very strong electrophile and a relatively weak nucleophile can now proceed in reaction. So we're going to see a reaction that looks like that. So we're going to form a ring. So if I were to count my carbons, this is very important whenever you're doing ring reactions, is to count your carbons. 1, 2, 3, 4, 5, 6. So we're expecting a 6-membered ring. So if I drew that over here, I would have 1, 2, 3, 4, 5, 6. And we're going to expect a mixture here. So I'm going to draw 2 of them. And we see that at carbon number 1, we can attack from either the front face or the back face. So I'm expecting either a hydroxyl group on a wedge or a hydroxyl group on a dash. okay? And the remaining substituent is a CH2pH group. So, you know, if it was on a wedge, then we would have PHCH2, and over here it would be PHCH2. Okay, so you have this racemic mixture at that position. And yeah, so let's move on to part 6, I guess, number 6 over here. So we now have this amine adding into a carbonyl group, so we're used to this at this point. So the first thing I would do is classify this amine as a primary amine. So primary amines always form the imines, which is the carbon-nitrogen double bond. So I can literally just copy and paste my starting materials, and I can replace that oxygen with just my nitrogen with the associated carbons. So it's a 1, 2, 3, 4, or something like that. Obviously, you can draw your sigma bonds a little bit more nice. So that's number 6. All right, so let's look at number 7. So number 7 is a hydration reaction with this ketone. So be cognizant of the side information that we're giving you in these problems. So let's just look back to number 6. I showed that we're subtracting water. So that means I am driving the equilibrium all the way to completion. In number 7, notice how we don't have a lot of information here. All we have is that we're adding in water to this ketone. So let me just show the end product of this before I comment any further. So we would form this gem diol from the hydration reactions. Okay, and that gem diol, remember we talked about the steric hindrance that is associated with forming this product. We have this hydroxyl group adjacent to another hydroxyl group, adjacent to a ring, this R group and this R group. So that is very, very unstable. It is not favorable. We prefer this carbon-oxygen double bond. So, and there's no additional stabilizing features like removing water or anything like that. So we would actually say that there's no reaction here because the equilibrium is not driven to completion. All right, hope that makes sense. So that was like the one trick question in this worksheet. So number 8, we see another amine nucleophile that we're adding into a carbonyl group, more specifically an aldehyde. So the first thing I want to do is classify this. So that amine is a secondary amine, so we're expecting an enamine product. So that's the carbon-carbon double bond with an amine next door. So I can just copy and paste this starting material. And I can replace, excuse me, I'm doing the wrong thing here. And I'm just going to draw a single bond with the nitrogen and the associated structures, but I'm not going to draw that in right now. I just want to show where the double bond would be. Oh, I'm sorry. This is in imine. My bad. This is a primary amine, not a secondary. My bad. I apologize. So a primary amine is going to make an imine. So that's the carbon-nitrogen double bond. So that's actually easier. I can just draw my starting material again, and the end product is going to be something like this. Now, I do want to point out something that Dr. Peterson wanted me to point out to you as well. So it actually matters the orientation of this triangle or the wedge. So see how you can basically draw it this way, or and I'll just show the alternative that is wrong. So do not do this on your test. Okay, so see how like the larger piece of that triangle faces the nitrogen on this example over here, and on this example it's the smaller piece of the triangle? Well, this triangle, so we remember that the hybridization of that nitrogen is sp2, so it's trigonal planar, so it really shouldn't have any stereochem. But the wedge at this configuration basically signifies that it's this group that is being the one that is not in plane. And if when you look in comparison to this one, where the origin of that triangle is, that's where it shows the stereochem. So this is basically saying that the nitrogen is out of plane, and we don't like that. So this is the right configuration, showing that the methyl and ethyl substituents attached to that nitrogen is the stereochem there. So this is the right answer, not this. All right, let's move on to number 9. So again, we have an alcohol-based nucleophile located in a chain in close proximity to a carbonyl group. So that should immediately think intramolecular ring closing. So if I were to number my carbons here, I have that. And the purpose of the acid, again, is to protonate that carbonyl to make it more electrophilic. So if I were to draw a ring, okay, so look, carbon number 3, we didn't play with any stereochemistry there, so I'm just going to leave the wedges of the methyl groups. And then carbon number 6, I can attach from either the front face or the back face, so I would expect either a hydroxyl group on a wedge with the methyl on a dash, or the opposite. So we have a mixture of diastereomers in this case. So something like this. Sorry for the clutter. These are a mixture of diastereomers at that position. All right, so let's look at number 10. So number 10 is classified as a secondary amine this time, and it's going to form an N-amine, so a carbon-carbon double bond with an associated amine. So if I just copy and paste my starting material, so I need a little bit of room for this one, it's going to be and we are going to have this nitrogen here, and I'm just going to bring everything else for the ride. Alright, so now I need to figure out where I'm going to put that double bond. So I have a regioselective choice about where I can put this double bond. So I can, and you'll see it in the mechanism of why we have this regioselective choice. It's basically there are two beta positions from that amine that we can, remove protons from, so either this position or this position. And we want to remove that proton to form that Zaitsev alkene, if you remember from Orgo 1. So we can either choose to do it, I guess in this position over here or this position. So we obviously want to do it here where we have a di-substituted alkene versus just a mono-substituted alkene. So that is our end product. Okay? So let's look at number 11 and 12. So these are actually one of my favorite reactions. I know they seem funky, but they're so cool. I suspect you will have something along the lines of this in synthesis, so we will talk about that when I do the exam review videos. But these 1,2-diols can be used as protection groups for the carbonyls, and I won't talk about all the details now. We'll talk a lot about that later. But basically what happens is they react like alcohol nucleophiles. So I could basically just copy and paste this chain, and your product is going to be something like this. So if we were to count the atoms in here, that is 1, 2, 3, and 4. Okay, so it forms this kind of crazy cyclic ring, and we'll talk more about that in the review video. So, and again with 12, so the opposite of 11 is 12. So in 11, we are adding in a 1,2-diol under acidic conditions and removing water. So in number 12, remember, we have this acidic catalyst as well, but now we're adding in water. So that's going to remove that. It's the hydration reaction. So we are going to see something like this. Okay, and that is the end of Exam 2 Worksheet 1. Again, I apologize for the video not uploading onto Canvas, but hopefully it'll be all fixed on Tuesday. And as always, email me with any questions.